Okay, so now I begin lecture 24, Monte Carlo simulation applications. This is NE402, Intermediate Nuclear Engineering, Diffusion and Transport of Radiation and Monte Carlo simulation. And I will now be covering Godiva and Clark's criticality experiment. So this is an application of Monte Carlo simulation. Okay, so first thing I want to say to you is that I'm going to be running the simulation for one neutron as a source neutron. And when we have a critical system, then we make it critical for a certain energy level, for a certain power level. Now the power level could be 50 watts, a small assembly, 100 watts, 60 watts, 80 watts. So at every power level, we have to calculate the source term separately based on the power. So the tallies that you get should be normalized to a power level. Okay, so let's run through a very basic thing that 1 electron volt is 1.6 times 10 to the minus 19 joules. It's a very small amount of energy in electron volt. Remember I told you, you rub your hands and you get a few million electron volts. So it's the electrons, it's the energy corresponding to an electron going through a voltage of 1 volt. So it's a very small amount in terms of joules. And let's assume that one nuclear fission reaction gives you 180 million electron volts of energy. So in terms of joules, it's a very small amount, 180 times 1.6 times 10 to the minus 13 joules. That means that 1 watt is the inverse of that. So 10 to the 13 divided by 180 times 1.6 fissions per second. And let's say that one fission from U235 results in 2.5 neutrons. So the source term for 1 watt would be about 8.6806 times 10 to the 10, which means that if you're running Godiva at about 100 watts, then you've got to multiply, you're running with 8.68 10 to the 12 neutrons per second. So this becomes your normalization factor for the source neutrons. Okay, now let me take you through the MCNP input file. This little sketch I've got here is to show you the picture. It's a sphere. Godiva is a sphere. It's a bare sphere of radius 8.7408 centimeters. So just put your hands that big, so about 17.5 centimeters is the diameter of the sphere. So just by your hands, get a feel for how big it is. Okay, so we have a source of neutrons inside. We're going to simulate the histories of each of these neutrons. We're going to see what its K effective is. We're going to calculate, simulate the leakage in the blue arrows going out of its boundary. And so if you look at this input file, it's got 3 blocks. The first block, the second block, and the third block. The first block, the first line is a title line. You can write whatever you want. And in the old days, we used to have cards. So I'll also say cards and the manual say cards. So we used to have 5 spaces, then 1 space. So that's 6. And then 80 was the full card. So 74. So you cannot go more than 80. Right? And MCNP would give you an error if your line becomes very big. So this is the first block, which is telling you that the first cell has material 1 with a gram density, because it's a negative number. It has a gram density of 18.74 grams per cubic centimeter. It has a negative sense with respect to surface 1. Surface 1 is a sphere centered at the origin, 8.7408 centimeter. Anything after the $sign is a description, Godiva sphere. So cell 1, the volume region, this cell 1 is inside the sphere. Cell 2 has a positive sense with respect to surface 1, so it's the outside world. And it's got a void. So although there's air, so I'm saying there's vacuum. Okay, because not much interest in the outside world, outside Godiva. Okay, so Now, the second block gives you the surfaces. Now, this problem has only one surface. So surface number one is a sphere, that's the mnemonic, and 8.7408 centimeters is the radius of that sphere. Now let's come to the third block. The third block, the first card is a K code card, which tells you that it is a criticality calculation. You can run MCNP in a criticality mode, or you can define a source by SDEF. The SDEF card defines a source. So here we take a very special kind of a source, which is K source, which begins source neutrons at the origin. X is 0, Y is 0, Z is 0. Its energy sampled from a Watt fission spectrum. And the parameters, the options that I'm specifying with the K code run description is that I'm going to simulate 1,000 particles. My guess for K is 1. I'm going to skip 20 cycles, and the total number of cycles I'm going to carry out this simulation for is 120. Now, the reason I take skip cycles is because I expect lots of fluctuations in the beginning, so I don't want those fluctuations to spoil my estimate at the end of the mean and the standard deviation. So it's a good idea to skip a few cycles. So let it stabilize and let the power distribution stabilize. So 20, 25, 30 cycles would be really good to skip. So this is not a big simulation I'm doing. Otherwise, I could say 10,000 for 1,000 cycles. But that would take a lot of computer time. Okay, so here's a comment card that in K code, fission is treated as an absorption. So what K code does is that neutrons are started, and they're started at this point, 1,000 neutrons. And the first time a fission takes place, it is absorbed, the particle is absorbed, and a new source particle is created and started and simulated. So every time a fission takes place, we mark the sites, and now we mark 1,000 sites where fission has taken place, the first event when fission takes place. So once you've got those 1,000 fission sites, you come back and you sample from those 1,000, start the second generation, then the third generation, then the fourth generation. And when you divide the children divided by the parents, then you get the system multiplication. So we've got the importance. Now what we're going to do is we define the importance. Now remember when we were discussing the importance function, I told you that we can set the importance to increase the number of collisions artificially somewhere so that we get better statistics. So in this problem, there are only 2 regions. So I'll set the importance of the inner region as 1 because I expect a good number of collisions. The second, I put it to 0 because as soon as a particle crosses this boundary and leaves the sphere, I'll just kill it, I'll stop it, I'll terminate the history, and I'll start something interesting inside the sphere again. So that's why it's a neutron-only simulation. Otherwise, you'd have to define photon importances also in :P. Again, the number of importances is the same as the number of regions in your problem. So M1 to M7 are the materials that I'll be interested in. And you can see that I have U235 and U238. So I'm not modeling U234 just to show you a simple simulation. Now, when I have a negative sign here, that means the weight percentage. So material 1 is 94.73% U235 by composition and 5.27% by weight of 238. And let's define these. We don't need to use them, but I'll carry out simulations that what if it goes down to 87%, that goes up, and this goes down to 50, then 70. So we'll try to do separate runs. That's what I showed you in the previous lecture. And then I'll define uh, some special materials here for tallying. And so these are the two tallies. Now in the MCNP volume, we've got tallies, as I told you, F1, F2, F3, F4, F5, F6, F7, and now F8 also. Okay, so F1 stands for current. So this is the neutron current leaving surface 1. Surface 1 is a sphere. So I'm interested in that. And F4 is the flux, the track length flux. And this is in region 1. I'm interested in that. Now I can multiply the flux by anything. So this is a comment card just for your interest, that the comment card for tally number 4. So I've got an outer bracket here and an outer bracket here. So I'm going to multiply these 4 tallies by this number. And what is this number? This is the number which is the atomic density of the material multiplied by the volume. And this is material 1, which is defined over here. -6 and -7. So -6 is the fission cross section, and -7 is the nu bar. So when the flux is multiplied by the microscopic fission cross section, then by the number of neutrons coming out of every fission, and when it's multiplied by the number density, because that's a microscopic, so it becomes a macroscopic fission cross section, then it becomes the number of fission neutrons produced per cubic centimeter. So if I multiply by the volume, so the number that I get from the first pair of, within the first, these brackets, is the number of fission neutrons coming out. Now, reaction numbers 16 and 17 are NXN, that how many reactions result in multiplication, how many result in multiplication. So that will give me the NXN reactions. -2 will give me how many absorptions I've got inside here. And -6 will give me how many fissions I've got. So each one of these 4 gets multiplied by NV for material 1. So you can guess that if I divide this tally by this tally, then I should get the nu bar for this problem. Now this is a segment divisor that in a surface I could divide into more than one parts if I'm interested to get more information. Now notice that I have not specified any energy bins. I have not specified any angular bins because I just want to keep it simple for you at the moment. If I wanted to, I could have put E4 and C4 over here for this tally. I could say I want the thermal. So I could say 2.5 E minus 8, 1, 4, 10, 20. So because energy goes in MEV bins. I could say C4, it begins from -1 to 0 to 1. So I could get the F1 going backwards and the F1 going forwards. Okay, now this is the perturbation option that I've got. So I can do a sampling. So MCNP carries out sampling for the derivatives and for correlated. It estimates from the correlated simulation and from the derivative sampling from a single simulation. It estimates the first and second derivatives. So as you can see, the PERT card, you can put any number with it, but it slows it down. So the PERT 1 for neutrons. So in the first problem, I'm studying that if I change cell 1 to a density of 20 grams per cubic centimeter from 18.4, and MCNP has got 2 methods, 1 and 2. So method equals to 1 is the first and second order Taylor series, and it gives you only the change. Method equals to 2 gives you only the first order change. If you say -1, then it adds the change to your previous k and it gives you the new estimate for k. So this is what happens that if your density is this much, but you replace material 1 by material 3, so material 3 is defined. So if I replace 94.73% U235 with 50%, and similarly I increase U238, then what is the perturbation estimate? So you see, these would have to have been 8 separate runs, but I'm going to try to do them in a single run. And the print is the last thing in the third block. I'm going to print the results in tables so that I'm going to see everything in great detail. So that ends the input file. Okay. Now let me take you to the detailed okay. So let me do a new share, and the new share I'll do is to show you the output file. Okay, so I hope you can see this output file over here. So this is the output file that we get, and it's a huge file, and it gives you a lot of information. So I think this is the best code in the world, and it gives you things so nicely that I have not seen a better code for neutron photon transfer. Okay, let's go through this in great detail. So this is MCNP version 5. It's distributed over here, and with University of California, Los Alamos National Lab. So this is the first thing it tells you, that this is MCNP version 5. This is the ID, and this is the date I ran this at this time. So I ran it on June 25th, 2020 at night, 11:48, 56 seconds. This is the problem ID. Okay. So the first thing, this was my input file. It reproduces my input file. So these are all the lines. It gives me lots of warnings. For example, material 2, it says I'm not using in this problem. Never mind. Material 3, I'm not using. 4, I'm not using. 5, 6, 7, I'm not using. 1 is the tally. 4 is the tally. Comment. It accepts everything. Then it says that it's going to take an initial source from the K source card. The original number of points that I gave. You see over here, it says the table number. So you can read the MCNP volume 1, 2, 3, and they describe the output tables in much more detail. So I'm just taking you through it. So it says that out of these points, how many are not in any cell? So if I had made a mistake, so it would tell you, how many were wrong. But points not in any cell are 0, so I'm okay. Points in cell of 0 importance, there's no cell in 0 importance, that's okay. Void cells, no. Ambiguous cells, no. How many are rejected? 0. So MCNP has accepted my source, and I'm going to take 1,000 of these after expansion or contraction. So the population is going to remain fixed. The initial guess for K effective is 1. I gave that. Then I told MCNP to skip 20 cycles, and I said that you can store 1,000 histories. Okay. It says in the comment, the total fission, okay, the total fission nu bar, that means, that neutrons are prompt and delayed. So there's a small delayed fraction. So if you want to stop the delayed neutrons, then there is a TOTNU card, .nu card. But right now I'm taking prompt and delayed. Okay, so it says it's going, I've asked it for tally 1, and across surface 1, I've asked it for tally 4. Now when it gives me a warning that I'm using perturbation, so in the multiplier tally, because the number density might change, so it says that you may require a negative constant. Negative means that pick the actual density from the cell, but if it's a perturbation, then don't pick the density, leave it per density and multiply it yourself afterwards. Okay, in the post-processing. Now, these are the multiplier bins. You can see these are the number densities. So this is the material number. These are the reactions that I had asked for. This is the VM, NV number, right? 134.22. This is sigma F, nu bar. This is NXN. This is absorption. This is fission. Now it says the material composition, the sum of the fractions of material is the sum of fraction of materials. Okay, so it's material 3 is 100%, material 1. Material 3 is defined as 100% because remember 95 plus 5, 90 plus 10. So all these are okay. Now it calculates for U235 for each material 1345 the atom fraction. So I'm using material 1. It has an atom fraction of 0.947931 U235 and 0.052069. Now this we went through in one of the earlier lectures of this course when I taught you how to calculate the number density. So this is what MCNP does for us. Okay, so this looks right. Then it calculates the mass fraction. This is what we had given. This looks right. And it gives you some warnings. And here is the cell. So it calculates, you gave the atom density. The second is 0 because it's the outside world. 18.74 is the gram density. I didn't give any volume, so it calculated for a regular surface. It calculates the volume. It calculated the mass of my material. So you can see the mass is 52.4218 kilograms because this is in grams. This is in gram per cubic centimeter and this is in grams. Okay, so it calculated the surface area because it's a regular surface. So this is 4 pi r squared, where r is what we specified, 8.7. Okay, the cell temperature. Now we're doing this at room temperature. So at room temperature, the energy is 0.0253 EV. So in terms of MeV, it's 2.53 10 to the minus 8. So you can change the temperature because the cross-section libraries have cross-sections at different temperatures. So if you're doing a reactor core, which is at a very high temperature, so you give that high temperature and it will give you the cross-section at that high temperature. Okay, so here's the random number generator. Remember, we went through this in great detail in the course. The example I gave you was for an LCG, a linear congruential generator. So this is the seed, the multiplier, the number of bits used, and the stride. Now, the seed is the starting. So if you use the same seed, you can reproduce your numbers. But if you do not use the same seed, you cannot reproduce your numbers and you get a different answer. Okay, now these are the physical constants inside MCNP. A number huge is defined as 10 to the 36, pi, Euler constant, Avogadro's number, atomic mass unit, speed of light, Planck's constant, hc, neutron mass, and electron mass. The fission Q values, remember the Q values for all these fissile actinides are positive numbers. So this is the difference of the kinetic energies of the product minus the reactants, or the other way around for the rest mass energies. Okay, now these are the cross-section tables that MCNP is going to use. So you can see that it's going to use the NDEF 6 file, evaluated nuclear data file, number 6. The version is 5. And so for U235, it's actually going to use this data set, 92.235.66C. Now, I did not specify this, so it picked it itself by default. The length of this table is this much, and I'll talk about this in one of the lectures, that how do you know which data is lying where. Actually here, you don't need to know because MCMP is doing it itself. But you should have some idea, so you should study NFB formats, and I've got a chapter of that in the book, so I'll take you through that. So Enjoy is used as the processing code, the total new is used, and this is this version. And you can see that the probability tables are taken from this value to this value. Okay. And you can see that U238 is also being taken from the same 66C. C stands for continuous cross-section table. There's also a D for discrete. So this is U238 at about 20 degrees Celsius, 20 Celsius, which is room temperature. And this is the version. And so it tells you now run tape. In our days, we actually used to have tapes. So, but you don't now see the tape, it's your laptop actually. So the first dump it's going to do on RNTPE, the next on RUNTPF, then G, and so on. So the simulation begins. The number of particles sampled is 0. So far, no collisions have taken place. The computer time used is 0. The number of random numbers generated to this point, 0. Source tape that will be written is SRCTP, and this is, we're just about to start the simulation. And so far, you spent this much time running MCRun. Okay, so let's begin. Now, MCNP shows you the first 50 histories that it starts. Now, look at this table. So it tells you a lot. It tells you that the first 50 points sampled were all at the origin. So for each one of these, the XYZ is 0 because I specified that you started at the center. And each one of these points, the cell it lies in is given here. It's not a surface source. Now these are the direction cosines at which this source is going to be started. Now I told you that this is omega x, this is omega y, this is omega z, and if you go back to one of the lectures, you'll see that I drew a solid angle diagram. Okay, the energy is sampled from a Watt fission spectrum, so you can see that each neutron has a different energy. Each neutron begins with a weight of 1, remember? This also we went through a little exercise, and it begins at time 0. So you can do a time-dependent simulation also. Okay. Now these are the cycles that are going to begin the 120 cycles. So you'll see a lot of fluctuation in the first few of these. So see, cycle 1 gives you a collision value of K of 1.36. What a bad estimate. And it gives you a prompt removal lifetime in seconds. Now this is the between collisions, the time. So it's the time divided by the fraction that were absorbed. So, and these were the number of source points generated, okay, in cycle 1. So these should be about 1,000. Okay, cycle 2, quite different from cycle 1. It gives you an estimate of 1.133. Cycle 3, 4, 5, you see it's still stabilizing. And I hope that by here, things, well, it looks like I should have said 30 skip cycles. But, okay, so now begins our serious simulation. So it's giving you the estimator for K collision, K absorption, K track length. And here it gives you the simple average of collision and absorption estimators. And it gives you the absorption and track length. Okay, you'll see this in the next cycle because it's going to take an average of 2 cycles, then of 3 cycles, then 4 cycles, then 5 cycles, 6 cycles, and we'll reach the end like that. So 3 estimates which you can do yourself in a small program that you write. This is the correlation, because it's very important for us to see how they correlate. And cycle 23, 24, 25, you can see that there are roughly 1,000 points generated in each cycle. It goes on and on, on and on, on and on, on and on, till you come to what was specified. Okay, now when you come to 120, here, so you've come to 120. So our simulation is done now. Okay, so you get the collision estimator as 0.969628. You get the absorption as 0.971053. You get the track length as 0.9976. You see, they're all different. So here you can see the average of 100 cycles. This is the cycle estimate. So the average, you can see there's good agreement between them. And whenever I see 2 decimal places here, I say it's correct. So the estimate is good, we take it. If it was 0.3 or 0.4, I'd say it's a bad result. But this is a very good result. This is the relative standard error. Now these are the combinations of simple averages, and they look very good. So it's about 1. The answer is 1. Right? Okay. So the first source distribution is written here. I can do a continue run simulation, but no need to. Now let's see the summary. Now on the summary, you see one side over here and one side over here. So this is the creation side, and that's the destruction side. What was created? Let's see that we started 100,000 tracks, right? 100 cycles, 1,000 each. The weight we gave to each was 1. The average energy was 2.0663 MeV. And the weight cutoff, when the more and more collisions, so it used a weight cutoff like this. I didn't tell it to, this is defaulted MCNP. The other exciting thing happening is the creation by the NXN, the multiplication. So it produces 883 tracks like that. They have a small weight, so it's 1,000th almost, 1/200th of the starting weight. So there is some creation. Can you see? It should have been 1 if there was no creation. So there's a creation over here, and there's a little bit higher energy than what you started with. Okay, now where's the destruction? So this number has got to equal this number. So you started 1, you produce some by NXN. You see, now where would you get these estimates from? So this is such a wonderful simulation. So this is 1.0397. Now 1.0397 are destroyed by so many by cutoff, so many by loss to NXN, but mainly by, you can see over here, by escape. So about 57% of the weight has escaped. And that much energy, roughly that much energy per source particle has left the Godiva sphere. How many neutrons did we bank? About 530. Per source, we started 1.0088. Number of collisions. Now this is very important. About 4 collisions took place per source particle. Okay, so you can get an idea of the mean free path. How many collisions took place? 409,000. Okay. So if I divide this number by 100,000, so I get about 4.09, which is this number. So not bad. Per neutron, I got 4 collisions. This is the net multiplication of the system. So if I take a U234 and the better estimate, I will get 0.9999. So this is the cutoff time, cutoff energy, the weight cutoffs by default. And let's go to the tallies now. You can see the neutron activities. These are very interesting, that what really took place in the first cell. So with this, you see, MCNP tells you the nuclide activity, that how important was this. So out of these 2 collisions, where can you see more collisions? U235. So this was more active. Why? Because this was highly enriched. So there was very little U23. So look at all these and look over here. Okay, now let me quickly take you, these are all confidence levels, looks good, and read all these, but let me run to the tallies. Did I miss the tallies? No, the tallies are coming. So these are the removal lifetimes. These are the predicted changes in K effective. You can see all the perturbations. Now the first numbers were the change, and one of these adds up. So I think this one added up and gave you a big number, 0.67. Okay, so you can see what happened. And actually I'm trying to come to the tallies. So lots and lots of statistics over here. These are very useful charts showing you, see how they stabilize over here with this vertical line. And this picture tells you are you going right or going wrong. So look at the confidence level, so good. So in some problems, you may not get such good confidence level, like a shielding. So those are difficult problems. Okay, so you can go through all these, lots of statistics. Okay, now here's my first tally. The first tally, how many cross the surface, tally 1. You can see it's 57%. So 0.57242 is the fraction escaping. And here's the relative standard error, less than 1%. So 0.18. So I'm really happy about it. Okay, let's see the flux. Now here's the flux tally. Okay, now remember the flux tally was multiplied by NV. So the first was multiplied by sigma F, this is the volume, multiplied by nu bar, and C, this is what I get. Okay, and this is what I get for NXN. This is what I get for absorption. So remember, absorptions are about 4.47%. Now this is the number that I get. So if I divide 1.00165 by 0.38, so I should get the nu bar. Okay, so I didn't do that calculation, do it yourself, and divide this number by this, and you should get 2.5 something. Sorry, by 0.3855. So divide 1.00165 divide by 0.385581, you'll get the nu bar. Okay, so everything looks good, very good, and lots of information. Now this is a very simple problem. This is the effect of the perturbation. Can you see the surface tallies have changed? There's a little change. It's telling you that when you did that perturbation, then through surface 1, the F1 tally went down. And in other words, the escape became less. Okay, so this is for all the perturbations. Okay, so this goes on and on. Okay, so now let's go back to what we were doing. Okay, so let's have a new share and let's come back. Okay, so I very nicely showed you, taken you through the output file. Okay, so you see that this little input gave us all that output. Now, if you run a fixed source problem, then you can define your source by an energy distribution D1. That's the probability of D1 watt fission spectrum. There's some special, you can see the manual, they're built-in functions, built-in source functions. Now the X, Y, and Z of your source could be sampled from distribution 2, which says that sample it between X between -2 and +2. And this is a source probability for X. This is the source probability for Y. So you can sample it in a cube. Okay. Now, these are the results that for Godiva. that this run gave me, that if I started with this composition, and this was the K effective, and I studied all these changes, and I got the predicted changes from method 1 and method 2. Method 1 had the first and second derivatives. Method 2 had only the first derivative. So you can see that I so beautifully, MCNP gives the change predicted is like 33%. It says that, and if you do an actual rerun, it's 0.71. So yes, the answer is about 0.3. So this is a good prediction. So you see, out of one run, we got 5 results. And you can see that the predicted change was 4% when U238 went up from about 5% to 13%. And the actual change was 4.167%. Predicted was 4.356%. This is the difference between predicted and actual predict. You see, so the error becomes larger for a bigger perturbation. That's what we went through. Okay, now let's look at another experiment which Clark did in 1966 on, took cylinders, and this is the reference you can pick out of there. So basically looked at the influence of the distribution of, I think what I'll do is that we'll begin the next lecture from here, because this is, this should also take about 40 minutes. So I think I'll stop here and come back in the next lecture.